Hello and welcome. This is Mr. Buss, and I'm going to walk through this pretty cool statistical analysis that we did today in class called chi-square. Chi-square is similar to when we calculated deviation with our penny flips a while ago, a week or so ago, and it's just what it does is it gives us a better analysis of how far the deviation is from expected. So if you remember from the penny flips, our deviation, if we had a 50-50 penny flip observation, then our deviation would be 0. But if we had like a penny flip where we got like a lot of heads and not many tails or something like that, our deviation would approach 1. So it's similar to that, but it's different, okay? Similar in that we still have observed values that we're going to work with, and we're going to have expected values that we're going to work with. But we're going to do a little bit more math with those. We are going to take observed minus expected. We're going to square that now, and then we're going to divide by expected. And this symbol here, this goofy symbol, means sum of all. And what that means is that for every outcome, so like if it's a penny flip, you have heads or tails, you'd have to do this math twice. You'd have to do this math observed minus expected squared divided by expected for heads, and add that to, that's what sum of all means, observed minus expected squared divided by expected for tails. And so I think that the best way to explain this is just to walk through a few different examples of it. And so the first example is going to be a coin flip. And we'll use this chi-square table at the end of our calculations to make a conclusion, okay? So we'll start with a coin flip situation, and I took our values from a week ago, and 2025. And so I'll just choose an hour here. I'll choose hour 2, or hour 3, I mean, just randomly. So I'll use that data. Instead of using the totals look amazing. Like, wow, really close heads and tails, like 1,657 heads, 1,643 tails. I mean, that's really close to 50-50, right? But I'll just use hour 3s here. You could use any of these data sets, including the total, to do this calculation. So maybe I would even recommend that after I do the video, maybe choose a different hour and try it. So our first thing that we have to do is like know that these are observed values, okay? So our observed heads is 433, our observed tails is 407, okay? So what is our expected? Well, all we know for expected so far is that expected, if it's a fair coin, right, that you expect half of them to be heads and a half of them to be tails. And so we get the ratio, like we know what we expect, but we have to do the math to then see, okay, how many actually do we expect from this trial? So what we have to know first is the total. So the total is 433 plus 407, and that's going to be 840. And so you say to yourself, okay, well, if we had 840 total flips, how many do I expect heads? Well, half of 840. So you basically apply the math of 840 times 0.5, or 840 times a half, and that's going to equal 420 heads expected and 420 tails expected, okay? So now we can do this because that's all we really need to know. We just need to know observed and expected. So let's use our formula here. So observed minus expected squared divided by expected for each. So observed heads is 433. Expected is 420 divided by expected. And because this is the sum of all, we add that to the other. So we add that to the tails one. So tails is observed 407, expected 420, square that, divided by expected. So then let's do that. So 433 minus 420 is 13 times 13, so square it, is 169 divided by 420 is 0.4 plus 407 minus 420, negative 13, times negative 13, basically squaring it. 169 divided by 420 is another 0.4. So it's not going to matter if it's a negative or positive, because when you're squaring it, you get a positive. So 0.4 plus 0.4 equals 0.8. So our chi-square value, and that's what chi-square is. It's that curvy x squared. So our chi-squared value equals 0.8, and you leave it like that. You don't take the square root of anything. You just leave that. You don't have to do anything else. We're done solving it. Chi-square is 0.8. So now we have to evaluate that number, and we have to make a conclusion about our data. So again, our assumptions is that we expect normal flips, and coins are two-sided with equal chance to land on each side. And we use that assumption to get our expected values, right? We use that assumption and built it into the math here. Okay, so we're going to say, is that what happened? And how we do that is we compare our chi-square value here to the critical value in the chi-square table. And so we have to figure out which number to compare it to. And so in order to do that, we need to match up our columns and rows. And so usually in the problem, it will tell you which p-value to use. So we're going to use a 95% confidence interval, which means that when we make a conclusion, we're 95% sure that our conclusion is right. And that's just, I know that sounds weird, but that's how statistics works. You come up with a confidence interval. Very rarely or never will you see someone say, I have 100% confidence. That would be, usually you use 95% confidence to make a conclusion, or even 99% confidence. So we'll use the p-value of 0.05, so we'll use this row. And then which column do we use to match up our numbers? And so that's the degrees of freedom. And so that we have to think about. And so degrees of freedom is equal to the number of possible outcomes minus 1. So in a coin flip situation, there's 2 possible outcomes, heads or tails. So 2 minus 1 equals 1. So we have 1 degree of freedom. So we are going to use the number 3.84, because that's the match of our column and rows. So 3.84 is our chi-square. It's called the critical value. So critical value is 3.84. Our chi-square value is 0.8. 3.84 is greater than 0.8. And so when our chi-square value is low, that means that, like with the deviation, as we did in the penny flip, when we have a low deviation, then our numbers are what we expect. When we have a high deviation, then our numbers are not what we expect. So since we have a low chi-square value as compared to the critical value, we say that our null hypothesis, which our assumptions were built out of, is probably correct, okay? Now, another way to say this, and I know this is going to sound goofy, is that is like saying the opposite of that would be, but like saying the same thing but differently would be to say we fail to reject the null hypothesis. I know that sounds weird, but it's basically saying the same thing. You're saying the null is correct, or you're saying we failed to reject the null hypothesis. That would be the more appropriate way to say that. Both of them are kind of saying the same thing. I'm going to stop this video because it's going to get kind of longer otherwise, and I'm going to then pick up with part 2, the chi-square M&Ms, for a second video.